Hello everyone, I am Radha Kumari Pani, Assistant Professor at Vedang Institute of Technology. So far on we have discussed about the diffusion process in the different types of material, and also last class we have discussed the one is Kirkendall effect and the Fick's law. And what Kirkendall effect says? It says if two different metals, two different composition of metals, if we anneal together or mix together, another alloy is formed, okay, in between the two metals, and the one term that is parameter, that is flux, okay. We have discussed, and also we have derived the formula for the flux, that is flux is directly proportional to the concentration gradient. And also from the Fick's law also we have derived one formula, that is flux is like the number of atoms crossing per unit area per unit per time, okay. So J is equal to d dc by dx. So in today's class we are going to discuss about the atomic mechanism of diffusion, how the diffusion process, okay, is carrying out in the atomic level. We have not discussed till now, but it is very important to know completely the diffusion process in metallurgical science, in materials, how the diffusion is carrying out in atomic level, and what are the mechanism and what are the driving force behind this process, okay. So generally this diffusion in the atomic level carrying out by two pathway, or we can say by the two mechanism. One is substitutional diffusion and another one is interstitial diffusion. So in the types of diffusion process also I have shown you the presentation how the interstitial diffusion is carrying out, how the substitutional. Interstitial means one atom is going to another interstitial site, okay, another vacancy site, that is known as interstitial diffusion. Also we can see here from this diagram, this known as interstitial atoms, and another interstitial voids or vacancy is there. So from this position to this position, the transition is known as diffusion, and the diffusion process is known as interstitial diffusion. Similarly, we can say the substitutional diffusion means the atom will go to its neighboring vacancy or neighboring empty position, okay. So like in that metal, we know, and every metals have some vacancy, have some empty sites. So if the atoms is going to that vacancy position, the diffusion is the like, if see, if this atom will go to this side, if let this is the atoms and this is the vacancy, if this atom will go to this voids, so what happens? In this position vacancy will be created, okay. So this is known as diffusion, and the process is known as substitutional diffusion. So generally, what are the elements that are present in metals? That can be carbon, oxygen, or hydrogen, okay. These are the general atoms that are elements that are present in the metals. So in interstitial voids, also in substitutional voids, so the diffusion is occur by some interstitial diffusion, because these elements like carbon, oxygen, hydrogen will go to some interstitial side, another side, so vacancy void will be created. Similarly, the vacancy are always present in every metal, so substitutional diffusion is possible without any driving force. If the atoms by some like thermal vibration or by some see, in every metal the atom will go some random vibration, there will some oscillation, so that it can acquire the enough energy so that it can cross the activational barrier and jump to the substitutional side. So this process is carrying out without any driving force, okay. So let's first consider the random jump of atom, that is diffusion without presence. This two types of diffusion is carried out without any driving force, like we are not giving any thermal vibration or we are not giving any excitation, but anyhow the what diffusion process will be carried out, because there will be some vacancy always there in metal, so that the substitute atoms can go to the neighboring side and create the voids. Next, see, interstitial here will conclude one point, that is interstitial diffusion is happen very fast, okay, is happen very fast than the substitutional diffusion. Why? Because see, atoms vibrate with the Debye frequency, the scientists Debye, okay, have discovered this frequency. This is known as like, this is the minimum energy we can say in, if in terms of photons, okay. This is the minimum energy, so that the particles can go to ground state to excited state. Every atoms have some minimum energy. So the atoms vibrate with Debye frequency at their position with average energy, that is 3 kT. K here it is your Boltzmann constant, okay, the energy is 3 kT. So because of some violent, because of some oscillation, or because of some randomness, so it can acquire the enough energy so that it can jump to the activation barrier. So that after the jumping, it will be create some void, and that void process, okay, that creation of void is known as diffusion. So, in context of atoms, atoms may be considered as aimless, brainless, or restless matter, which are always try to jump even without any gain or without any driving force. In interstellar atoms, see, the concentration of atoms is very less. If the concentration is very less, then the atom can go to any sites. Okay, the voids will be created more. There will be more vacant site. For example, we have discussed the carbon solubility in iron. Okay, we have seen that the carbon solubility in gamma structure of iron is more that of alpha, because in alpha only one octahedral void is occupied out of 3000 void because of mismatch of the size. Okay, mismatch of the octahedral void size and the carbon size. The carbon concentration in alpha structure of iron is less. So that in substitutional diffusion, however, the diffusion process is rather complicated, because we have to create some vacancy, because the atoms will exchange their position with the what vacancy side, so that, and the vacancy will be created near the melting point. Okay, the vacancy, the number of voids will be more near the melting point. So the diffusion rate in substitutional diffusion rate is much slower than compared to interstellar diffusion. So the interstellar diffusion will cover the interstellar diffusion, how the interstellar diffusion is carried out between the adjacent planes, and what are the parameter is left behind. Okay, so let us consider the three adjacent planes here. Three adjacent planes, plane 0, plane 1, plane 2. Okay, 0, 1, 2, and these planes have many voids. Okay, and the few voids are occupied by the interstellar atoms, and the concentration of interstellar atom is let C0, C1 and C2. The concentration in plane 0 is C0, and the concentration of interstellar atoms in plane 1 let C1, and the concentration of sorry, in the plane 2 is C2. And we have one assumption that the concentration the atoms in plane 0 is more as compared to plane 1, as compared to plane 1 than that of plane 2. Okay, if the concentration in plane 0 will be more, then that means the number of atoms, the flux, okay, the flux, the number of atoms will decrease from plane 0 to plane 2. Okay, because the distance between the two planes, from this to this and from this to this, is del x. Okay, the distance between the adjacent plane is del x. Remember, there is no driving force, there is no any electric potential gradient, there is no any chemical potential, but the atoms will jump to the adjacent planes because of some oscillation, because of some vibration. Because of some oscillation and vibration, it will acquire some energy, the minimal energy, so that it can cross over, okay, the jump, the activation barrier, so that it can jump. Let us consider first the jump of atoms between plane 1 to plane 2. Okay, let the interstellar atom jump between plane 1 to plane 2. So that what will be the flux? The flux J1 will be half N1 sigma 1. Here is the formula. Okay, if the jumping of atoms is carried out between 1 to plane 2, then the flux will be half into N1. Here N is the number of atoms, okay, the number of atoms in plane 1, and sigma 1 is known as the jump frequency. Okay, see, here the jumping of atoms will be happened, so there will be some jumping frequency related to that atoms. Okay, that jumping frequency is symbolized, is notated by sigma 1. So similarly we can also write what is the flux of atoms when it jumping between from plane 2 to 1. Okay, if the jumping is happening from plane 1 to plane 2, then the flux of plane 1 will be half N1 and sigma 1. Here N1 is the number of atoms present in plane 1, and the sigma 1 is known as the jump frequency. Similarly, if the jumping, okay, is happening from plane 2 to plane 1, then the flux of plane 2 will be half N2 and sigma 2. Similarly, N2 is the number of atoms in plane 2 and sigma 2 is the jump frequency in plane 2. So here we can see the term that is half is included here. Why half? See, because we have not sure, okay, the atoms that is present in plane 1, it will only jump to the plane 2. Also, it can jump to plane 0. Okay, there is some probability will be there. So, we'll consider if the two adjacent planes is there, half of the atoms will jump from plane 1 to plane 2 and another half of the atoms will jump from plane 1 to plane 0. There will be happening, there will be some possibility. So, the terms half is taken over here. Okay. Here it is written. See, the sigma 1 is the jump frequency per second from plane 1 and the sigma 2 is the jump frequency from plane 2 and N1 and N2 is the number of atoms that are present in plane 1 and plane 2. Also, we have seen the concentration is movement, the number of atoms in plane 1 will be more than of plane 2. The factor halves come from the fact because the half of the atoms might jump from plane 1 to plane 2 and might jump plane 1 to plane 0. So here, the resultant flux we can write J1 minus J2. Okay, J1 minus J2, it will be half of N1 sigma 1 minus N2 sigma 2. And consider the random jump of atom is happening. So consider sigma 1 and sigma 2 it is equal to sigma. So there is some possibility that each atom can jump to any of the adjacent plane is equal. So we can write sigma 1 and sigma 2 is equal to sigma. So here the concentration also we have no concentration is number of atoms per volume. So we can see the concentration of atoms in mole per meter cube in different planes, N1 by del x and 2 by del x for C2. So that in terms of N1 and N2 we can write C1 del x. So here why it is C. The net flux is half of N1 minus N2 sigma. Okay. So here the C1 is N1 by del x and so N1 can be C1 del x. Here C2 is N2 del x. So here we can write N2 is C2 del x. In the position of N1 N2 write C1 C2. So half C1 minus C2 del x will be common. It will be out from the bracket. So this is the formula that net flux is half C1 minus C2 del x into sigma, where C1 is the concentration of plane 1, C2 is the concentration of plane 2 and del x is the distance between two adjacent planes and sigma is the jump frequency. So here further the concentration gradient we know dC by dx, that is C1 minus C2 by del x or minus C2 by C1 by del x, it is the concentration gradient. So since the distance between the planes is very small, the same dx and dx is taken over here. So the net flux from the plane 1 to plane 2 can be written as, from the previous slide we have discussed J, that is half, from the previous formula J is half C1 minus C2 del S sigma. Okay, and the concentration gradient C1 by C2 by del X is known as dC by dx. So from here, see, from here the del X will be, from here, see, here I am writing the concentration dC by dx C1 minus C2 or by del X. Okay, so we can write C1 in the like in the position of C1 minus C2 we can write dC by dx into del X. Okay, so here we can write in C1 C2 we'll write dC by dx into del X sigma. So the final equation will be half, see, minus term will be there if I consider the negative concentration gradient. So dC by dx del X square sigma. Okay. So now comparing with the fixed fast law. Okay, what fixed fast law says? Fixed fast law says that the fixed from the fixed law we have derived that the diffusion, the flux is directly proportional to the concentration gradient. Okay, and here the proportionality constant, that is D. diffusion coefficient or diffusivity. So in the position of, okay, if J is equal to d dc by dx, so what will be d from here? D will be minus half sigma del x square. Okay, now from the fixed fast law, that is J is equal to d dc by dx, and also J is equal to this much dc by dx. So here d will be half sigma del x square. Okay, if we consider, see, this is the final equation, the relation between the jump frequency with diffusion coefficient. Now, if you consider the atoms can jump in the three-dimensional, see, in the three-dimensional, the atom can jump any side. Any vacant side it will see, it will jump over there. So, we will consider the coordination number of that metals. So, the final equation will be D is equal to sigma del x square into Z. Here Z is the coordination number, means the number of nearest neighbors vacancy side voids of the atoms. So, in FCC, in like face-centered cubic crystal, the diffusion coefficient can be written as minus d half sigma del x square into Z. Z is the coordination number. Okay. So now the active C, consider one cubic crystal is there. See, these are the interstellar atoms and these are the what atom, and these are the interstellar vacancy. So these atoms can jump to this, can jump over this position, can jump to this position, also can jump to this position. So you consider the diffusion parameter only at one point. So what will be the diffusion coefficient? That is sigma I del x square, where the sigma is Z sigma I. Okay, this is the formula for diffusion coefficient for FCC crystal. D is equal to sigma I del x I square, where sigma is Z into sigma I del x is the plane. This is the lattice parameter, that is the difference between two adjacent planes. So up to this today, up to this topic, okay, what is the how the diffusion coefficient is related to its jump frequency, okay, and how the flux also is related to the jump frequency. This is the important formula we have to remember, and in next classes we'll discuss more about this, and we'll discuss one formula. Also we'll solve different types of formula regarding this parameter, regarding this formula, how the diffusion coefficient is related to the jump frequency of that atoms. Okay, basically we have to remember, see, the jumping or the diffusion can be happen from any side, but in substitutional case it will be if you'll compare the substitutional with the interstellar diffusion, the interstellar diffusion will be more, because in substitutional diffusion atoms will going to exchange their position with the empty or vacancy side. So we must have some vacancy position. Also from vacancy is created near the melting point. If I melt one material, then the vacancy site will be created, and this process will take over more time. Okay, so the interstellar diffusion will be more than the substitutional diffusion. And same, if you consider the adjacent planes in the interstellar diffusion, there will be jumping will be happen from one plane to adjacent planes. Okay, from that we have discussed what is jump frequency and how the diffusion coefficient is related to this, and what are the flux. So in next classes we'll discuss more about this topic. Thank you so much. Have a nice day.